Good morning, everyone. Good morning, good evening, good afternoon, wherever you are. So, I'm going to talk about the work on design automation for quantum computing. And it has two words. One is quantum computing. I believe I don't have to explain to this crowd, all of you know about it. And the design automation in any domain basically means when you are designing quantum circuits or computing using quantum computers, what are the software tools or automated methods that we can apply to reduce the manual effort going from all the way from applications to computing using quantum computers. So what I'm going to present today, here is a brief outline in the interest of the audience. Those of you are not from quantum computing domain, what is it in layman terms? And then I start with a quantum algorithm and then talk about how that quantum algorithm we can take through different design automation steps. What are the primary challenges in this presentation? As you know, and you are attending probably a lot of talks, you already know that there is a lot of researchers working. So I decided, in the interest of time, I decided to talk about one sample work for each of those topics. And I decided to choose Daniel's work for those, but I want to tell you that there are a lot of works in each of those domains. So it's simply I'm choosing one of my students' work as an illustration and in the interest of time. And as I go along, please ask me question. Whenever you have a question, please unmute yourself and ask, and instead of waiting for the end of the talk. So when you talk about quantum computers, so there are different types of quantum computer based on technology, whether it's the superconducting qubit, for example, from IBM, or whether it's kind of and it's a microscopic picture of that, or whether that's a trapped ion kind of qubit. Depending on what we are looking at, it may look and feel different. But the interesting fact is qubits are getting larger in size. Now, this is in deep contrast with what we know in the VLSI domain, that each of the transistors are getting smaller and smaller. When I was doing PhD 20 years ago, 18 micron used to be really called tiny because that's micron. And now people are talking about 5 nanometer, 3 nanometer, and nobody knows where it's going. So there was a 1,000-time reduction in, in 20 years in size, whereas qubits are getting bigger. And you might be wondering, oh, the fabrication technology cannot make it smaller. It can. Then you have to look deeper. Why it's getting bigger? So first of all, when you look at this quantum computer, it may seem like this, all of it is quantum computer. No, it's not. There is a tiny chip. I just, if you zoom in somewhere right here, a tiny chip, and this is the size of the finger, so we can figure out how tiny that chip is. That tiny chip is your quantum computer. Everything else is just everything else. So what those are, so for in the chip, whatever number of qubits you have, they would be connected through these wires, and all of these wires would be connected to your classical computer, FPGA board, all that, analog to digital, digital to analog, everything that's getting connected. And because these wires are whatever the size it is, the moment you had 2 qubits versus when you have 10, you need a lot of space to connect these wires. So that's basically the story here. So that's the interesting stuff. Now, in layman terms, what's the intuition of quantum computing? And this is the Daniel is in the audience in case you have any questions. So this is Daniel interpretation of how we looked at it. Let's assume I'm a rocket, or personify a rocket. So rocket has a state, which is a position and velocity, and which you can represent using some form of matrix. And then think of a headphone, your favorite headphone, maybe the Bose headphone. And then your headphone, or at least the expensive one, achieve noise cancelling with wave properties, constructive and deconstructive interference. And this can be used as a complex number. Now, if you think rocket as a human, it's really noisy. So put the headphone on top of the rocket. What we have is a quantum computer. So a quantum computer that has a state which can be controlled, and the coefficients of the states are complex number that can be constructively or deconstructively interfere. So this is, if you think, well, it's still not clear how it's different from classical, here is how it's different from classical. So in classical systems, we have transistors. You can view them as switches or on and off or 0, 1. We call them bits. In quantum, you have qubits, which can represent both 0 and 1 at the same time. And in classical, you put more transistor, you have more computing power. This power is not power energy. This is computing power. How much can I come? You put more transistors, it kind of linearly increases. Let's say you have 1 core versus 2 core versus 4 processor core. Expectation is you can perform 4 times better. But you and I know the program has to have parallelism. Compiler should be able to find that. Synchronization should be minimal. Of course, there are other things, but it's kind of a linear increase. But in quantum computer, the moment you put more qubits, it's an exponential increase. Specifically, if you have n qubits, the computation power is order of 2 to the power n. And if you're thinking, why is that? It's simply because qubits always like to talk to each other. They are social animals. Everybody is talking to everybody. That creates 2 to the power n. Now, that's good from computing ability perspective, but it's really bad from noise perspective. Now, those of you who work in classical domain and specifically dealing with noise, you may not agree what I'm just going to say, which is in classical computer, noise is moderate. There are noise mitigation, cancellation techniques, and you can deal with it. In quantum systems, because noise is also exponential, and simply because everybody talking to everybody, and they also want to talk to environment wants to talk to them, and it's just a chaos, big chaos. You want to compute something in a chaos, pretty much you get nothing out of it. Or managing noise itself takes so much of stress and energy, effectively you land up doing nothing. So handling noise is one of the major objectives in most of the design automation tools. And finally, in terms of applicability, now if they are kind of mutually exclusive, although it doesn't have to be. Typically, the things that are you are comfortable running on classical computers, you don't want to run them on quantum, or you don't want to try it. In contrast, the other classes of problem in optimization and different types of chemical and all that simulations and all that, those are very complex, very time consuming, or hard to get close to optimal solutions in classical that you want to attempt in quantum. Now, if you are an engineer, this is the difference from classical and quantum. In classical domain, we have a few logical gates, whether it's XOR and we can represent using truth table how different inputs. So this is A, B, C, and D, and this is X. How different inputs, different combination of values would represent different output. In contrast, in quantum systems, you have a quantum circuit using different kind of connections and Hadamard gates and whatnot that represent certain functionality, and you can represent them using unitary matrix. And as you can see, this is a matrix, but then there is this the I operator, which, if you recall, we talked about the noise cancelling headphone, constructive and deconstructive interference. This is what it basically represents. Now, in terms of what's happening with quantum computing, it started with a few institutes and with 2 qubit 20 years ago. And although this picture is a little old, but basically there is a steady growth in the number of qubits. And now we actually have a lot more than 128, which I tried to capture here. As of last year, IBM has 433 qubit computer. Now, those of you who are a fan of annealing and use D-Wave, they have thousands, but those are not generic qubits. You cannot do generic quantum computing using D-Wave qubits. They are specifically for annealing. So that I didn't capture in this horizon. I only capture the qubits where you can do generic computation. So what you see that from 2 to 433, or computation power 2 to the power 2 to 2 to the power 433, that's a huge increase in computation ability. But the noise is a serious problem. That's why today's quantum computers, we call them noisy intermediate scale quantum or niche computers, where we deal with noise or we spend most of our energy dealing with noise. In the future, we don't know when the future is, at least I don't know. When you will have 10,000 or more qubits, then we will be able to do reliable computing where we'll have enough qubits to do quantum error correction, fault tolerant computing. Now you would argue, well, if we have noise so much, what people are doing a lot of stuff. There are algorithms that are suitable even in a small number of qubits. So quantum sensing, quantum machine learning, quantum communications, there are many other applications that are flourishing or that are solvable using today's NISQ computers. But in the future, sky is the limit. You can do a lot of stuff: holonomic computing, storage, error, of course error correction would be integral part of it. All other hard or difficult problems you can solve. I want to briefly talk about quantum algorithms. When you hear quantum algorithm, if you are from quantum domain, you would think of Grover search or Shor's algorithm, and there are many famous popular algorithm. I'm not going to talk about those. I'm going to talk about an algorithm Daniel developed. And the reason I'm going to talk about, I want to walk you through a journey we took, why or how we developed that algorithm, so that when you are doing research, you want to develop an algorithm, you kind of have a yardstick. Oh, this is how Daniel used to do when he was developing this. So what we are doing is graph clustering. We wanted to solve using quantum computer. So we looked at the graph clustering. What is graph clustering to start with? It's a clustering in unsupervised machine learning. And if you look at social network like Facebook, the people who are following you, whom you are following, if you plot it, it looks a different cluster. And there are applications for it. If somebody is trying to pay certain amount of money to you based on how much royalty you bring to them, they want to know how many followers you have. Or whether the page rank algorithm used by Google to show you certain search, or the MRI machine when it's trying to look at the scan of the brain cells and trying to figure out if certain types of materials or chemicals are clustered somewhere, so then that's a sign of some tumor or cancer. So there are a lot of such examples of clustering. But the problem with clustering is the clustering has a cubic runtime growth in terms of number of nodes in the graph. And what is graph clustering? If you are not from computer science domain, so graph clustering is basically you have a set of nodes. Remember, in social network, each node is one person. Net of nodes, they are connected through either unidirectional edge. Let's say I'm D, I'm following somebody F, or it could be a bidirectional edge. Both parties follows each other. That's perfectly fine. We are trying to figure out the cluster where there is a strong connectivity and between weak connectivity. And the way spectral clustering works, you have a directed graph, then you do spectral analysis, and it's basically simple computation, and then you figure out certain nodes are of same close and other nodes are far. It's really figuring out a distance mechanism. So then you basically create adjacency matrix, you compute eigenvalues and eigenvectors, and you plot them based on that, and then you basically get your clusters. Now, as I said, if you have n nodes, you have n to the power 3 is the complexity of computing using classical computation. But you do computation using quantum, it's going to be in order n. All I'm going to say in next 1 or 2 minutes, what is the catch? Why quantum is able to do it in the order n that the classical takes order n cube to compute this? So before I do that, I want to, unless you are from physics, I want to take you to your physics or many cases chemistry book in your 10+2 class. So there would be a page where it shows hydrogen wave function. So all these numbers and all these pictures, just in layman terms, you are really looking at, you are looking at the probability of finding an electron. You can view it that way. You can view it as the magnetic field around the electron, whichever way you want to view it. So it's basically these wave functions we have, that's really the eigenvector. And if we can control any of these two wave functions, we have a qubit. Of course, today's quantum computers don't use hydrogen to construct qubit, but that's the basic idea. Why am I saying all this? Remember in the previous slide, I talked about computing eigenvalues and eigenvectors. These qubits have an interesting property. So when they don't do anything, they're talking to each other, they're actually computing eigenvalues and eigenvectors. In other words, so today's, for example, if you look at today's quantum superconducting quantum computer, it implements a qubit which can be viewed as up down arrows representing eigenvalues. And if you think of probability of finding an electron, that's wave function, that represents the eigenvector. Now, going back to quantum spectral clustering algorithm we were trying to develop, what we looked at, it's a really complex equation to compute eigenvalues and eigenvectors. When you give it to a classical computer, you are really translating all of these, writing a lot of function calls, whether in Python or your favorite language. When you compile it, it's a tons of binary instructions for that processor that you need to run to compute this. In contrast, now you think about qubits, if you can control it right, applying some pulse, and then you measure it, you are actually getting the eigenvalue. You don't have to compute all these hundreds of thousands of instructions to compute the eigenvalue, all these big summations, order of. So that's the order of n cube when you are trying to do this. And when you ask a qubit to do it, it's simply basically you measure it. Again, of course, I gave a layman terms interpretation. And here is the circuit of computing eigenvalue and eigenvector. Then you map it and you kind of get the story. So all I wanted to talk from here is that when you're trying to solve an application in quantum, you cannot run your classical algorithm. Then it will backfire. It's going to take longer than classical system. You need to have that application written in the form that are quantum friendly or taking advantage of quantum phenomena, whether it's entanglement or many other phenomena, you are taking advantage of it. Now that I talked about quantum algorithm, next I'm going to talk about briefly either for this quantum algorithm or any other algorithm or application you want to run using quantum computer, what are the steps it typically involves? I'm going to take some of the steps and what are the challenges, what are the tools, how do I run that tool, what's the input, what's the output? I'm going to give you that layman terms view. So at this point, do any of you have any questions? You can type on chat or you can just, it is better you unmute yourself and ask me. Okay, I move forward. So before I talk about any of these techniques, I mentioned that quantum noise is a serious problem. For the remaining presentation, I'm not going to talk about it. I just have one slide. I just want to highlight that noise is a major consideration, either for designing, for design automation, and there is a lot of work in the community on noise characterization, noise mitigation. And there are, so when people talk about noise, depending on whom you are talking to, some people follow Copenhagen interpretation, and if you're using QuCS, and so you are getting certain type of view or simplification or some form of abstraction of noise, which may or may not be accurate. Whereas some other community will be using Bohm's interpretation, and that could be more detailed, but again, it has its pros and cons, and depending on the situation, you'll use different ones. And we did certain work and evaluation of what exists on different work, how to look at this noise, and for developing algorithms, developing design automation tool. But when I'm going to talk about subsequent design automation objectives like quantum compilation, I'm not going to talk about noise again, but I want you to understand every optimization objective, every step compilation take, it's aware of the noise, it's trying to minimize the noise. And so when you're talking about quantum compilation, you have a quantum algorithm written in certain language. There are many specification languages. You compile it to a quantum circuit, and then you do pulse generation and run on quantum computer. This is same or similar to classical. In classical, you start with a C, Java, or Python program. You compile it to some form of uh, kind of representation, could be assembly, and then you generate binary. That's for software program. For hardware, you have VHDL Verilog description. You compile into a get level netlist, for example, get level or RTL netlist, and then pulse generation would be similar to you are just creating get level netlist or circuit or layout representation. Then that you kind of fabricate and put it as a ASIC. Only difference is in case of assembly actually runs on a computer, but you have a processor. In quantum case, you actually have qubits. You have to program the qubit to perform your computation. So the closest analogy would be qubits is more like FPGA than like processor. The way FPGA, every lookup table, you kind of program them. Similarly, when you start with the algorithm, you kind of map and choose and tell every qubit by through electrical pulse. These pulses are electrical pulses. You send electrical pulses, tell the qubit what to do, how to behave, or entangle two of them, or make them behave like a Hadamard gate. You have to send pulse so that they behave exactly the way you want. So while you are doing compilation, as I said, lot of optimization takes place. And one of the simple optimization could be compression. And so dimensionality reduction and register compression. So example would be, let's say you have a quantum circuit and it represents Q traits, but you figured out that the quality of result or fidelity you are looking for, qubit would be fine. So you are replacing all or some of the Q traits by qubits. That's how we reduce the dimension, reduce the compilation time and execution time. And then you can do register compression. For example, you can reduce the number of qubits and you still get the fidelity that you are looking for. So there are many such work out there on compression, and you can follow that and generate the pulses accordingly. I'm going to skip these. So here is an example to show that we are talking about a CNOT gate, and the behavior of the CNOT is, let's see, what's the behavior? If X is 0, then output remains the same. If X is 1, output is Y is flipped. So which is represented as Y plus S. Now, if I want to plot similar to truth table, this is how it's supposed to look. 1, 1, 1, 1, 1, and 1. Now, initially, let's say state is initialized, although I didn't talk about state initialization yet. Let's say this is how the qubits are, the way they are right now in the situation they are. And then once you apply the pulses, as you can see, electrical pulses, let's see if the animation works. So once you apply the pulses, then basically the qubits will go through certain transformation, and if things are right, something happens in this animation. It's supposed to be, this one is supposed to be yellow, 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 which is supposed to match with 1, 1, 1, 1, exactly the way they're supposed to behave. Now, grape or gradient ascent pulse engineering is one of the very common method of optimization. And when you are optimizing, you are starting with a random guess of what type of pulse should I generate. Then you solve the Schrodinger equations. Then you compare what you got and what you wanted. You wanted qubit to look left, but maybe it's looking towards right. So then you need to change your pulses, and while you are doing that animation, again something happened here, but anyway, so it's basically it's looking at the loss function and trying to minimize the loss function. You can think of minimize the noise. That's what it's trying to do. And here are some results that shows that if you kind of do compression on top of grape, then you can significantly reduce the pulse generation time without sacrificing the fidelity of the results. Before I begin quantum machine learning, any of you have any questions? Please unmute and ask.
So for the 3D plot you're just showing, is that the landscape for the loss function?
Yes. So this was the landscape for loss function. Daniel, do you want to add anything to
Yeah, it was like a 2D slice of, because there are a lot of parameters for the loss function, and so this is just taking two random slices or like directions in the space.
Yeah, so because I think in the optimal control you have many different channels to control the parameters. So this is only two of them, right?
Exactly. Yeah.
Got it. Yeah. Thank you.
Thank you. So now let's talk about.
I got
Go
one
ahead.
quick question.
Go ahead,
So
please.
for the compression, like what specifically do things doing for the compression for post generation part?
So if you think of pulse generation, right? So the kind of control, kind of quality, and whatever pulse you need to control a qubit rate, it's going to be much simpler, easier to control a qubit. Same thing, if you reduce the number of qubits, then the number of pulses or all of that kind of become much simpler for you.
I
So
see.
compression, it's similar to classical world. In classical world, what does compression give you? It takes less memory. It reduces your power footprint. It improves your cache hit ratio. But here things are different. But nonetheless, you are getting the same kind of thing.
I see. Thank you so much.
Well, you are welcome. Okay, so now we are moving to quantum machine learning. Now, this is one of the popular domain, very popular. Most PhD students, when they start working, they want to start on quantum machine learning because it has AI and quantum, two popular terms. Now, I'm not suggesting you don't pursue it, but I'm saying this is one of the popular area. Now, what kind of problems people are solving, I want to summarize and simplify it. So what they're really solving it, think of any quantum circuit. You put a lot of parameters there because you don't know what would work for the quantum computer because it is controlled by a set of crazy qubits. Qubits are crazy, trust me on that one. So then you want to have a set of parameters, and during you want machine learning to figure out what those parameter value would be for you to get the solution for the problem you are looking for or with the fidelity you are looking for. And one of the concrete example, if you are looking for, is that from Rigetti computing, this diagram I took, they're trying to do variational quantum eigensolver, a major component of a machine learning algorithm, if you want to think that way. They showed how classical and quantum computing can join hand to solve this problem. So quantum processor or quantum computer, if you think you want to have a state preparation, which I'll talk in a moment, and then you want to measure certain terms and pass it to the classical processor. And in this particular case, it's doing some ansatz computation, and then classical computes and gives the feedback. In layman terms, what does this mean? Quantum computing is doing some computation. Classical is reading the value. Based on that, machine learning is figure out, are you going in the right direction? Are you going in the wrong direction? Do I need to control some of the parameters to turn you in a different direction so that you can faster reach your target? And then that feedback comes in. The whole objective of this story is, how do I reduce the number of iterations? Can I do in one iteration? That would be ideal. How do I reduce the iteration? How do I quickly reach the target state? And that's basically kind of quantum classical hybrid story where some form of machine learning and quantum goes hand to hand. But in general, many of the community people, when they are working on quantum machine learning, they can completely solve only in the machine learning domain or classical machine learning domain, although they are actually solving a quantum computation problem. So I keep talking about quantum state preparation. That's actually important for no matter how you look at it. And let's just look from quantum computing perspective, but quantum state preparation is also vital for quantum sensing, quantum storage, quantum communication. You have to prepare the state. Otherwise, none of them will work. Let's look at in quantum computing. So input comes in, you prepare the state, then you kind of do the computing. So you prepare the state and map your quantum circuit to the quantum computer and all that stuff. And by the way, your state preparation also a part of your quantum circuit. So your quantum circuit is doing your actual logic that you want to implement, and state preparation needs to be a part of it. If you're thinking, what is state preparation? Think of it. You want a classical processor to do an addition. You cannot just send an add instruction, expect it to do the addition. You need to initialize the program counter correctly. You need to initialize the registers correctly. You need to initialize a lot of things correctly so that you give 2 and 3 and you expect a 5 at the output. Same analogy here. So you want to program qubit and prepare the state in a certain way so that when you compute and then you measure, you actually get something meaningful that you know. So it's basically in a context of state machine, you want to start in a known state and then you have a known or valid state, and then you want to perform some computation, then you can expect something to happen, assuming noise is under control. So basically, this is the state preparation. Although I showed it as a one-time thing, it may happen multiple times. For example, remember the previous story of classical quantum. You have to come back and prepare state, do something, computation, prepare state. So I'm just focusing on this state preparation, which is a part of a lot of places. And how does state preparation happen today? There are a lot of approaches. I'm going to talk about two broad ones. One broad one is passive reset. You basically let it cool down to the zero state or ground state. And basically, if I get angry, one way you want to handle me is like, okay, leave him alone and just don't talk to him. He's going to cool down. So that's basically the story. So, but the problem with passive reset is how long do I wait? And you have a lot of qubits. The environment needs to be significantly cooled. There is a cost of cooling. And also, it's not suitable for preparing arbitrary state. Remember, when I'm doing any computation, it's not always the case that I have to start with a reset state or ground state. I may want to start with some other arbitrary state. So you can't prepare arbitrary state using passive reset. Then you have to do passive reset, and then you have to apply some gates or some computation you have to do to reach the state. In contrast, active reset basically tries to do, they basically, instead of waiting and hoping something will happen, it measures the qubits. And then classical computer basically said, well, it's going well, going fine, keep applying pulses and changes the pulses and until you reach that state. So the fidelity may be imperfect, and also there is overhead because classical computer is involved in state preparation. And so what Daniel looked at based on some work that already existed, the idea of quantum steering, that you can steer a quantum computer to do certain things. And what we are trying to do, steer a qubit. So basically, once you kind of, if you have a state qubit whom you want to steer, then you want to start with an auxiliary qubit and start measuring it. If you entangle them properly, then simply the act of measurement will guide this qubit to where you want it to the target state or desired state. Now you might be thinking, well, you are measuring, so therefore classical is getting involved, so overhead is there. Answer is no. We are simply measuring. We don't care about the actual value, what we get out of it. The act of measurement or measurement induced steering is going to guide this system qubit where I want it to go. And so we do have a lot of work in terms of passive steering and active steering. But the key idea remains this. Now you might say, well, why am I not directly measuring and steering this qubit? Because remember, when you try to measure somebody, it collapses the state. I don't want it to collapse. I want it to reach a state, and by simple act of measurement of some. So I don't want to affect the reliability of this particular qubit. So that's the state. And here I talk about only one qubit, but you realize in the real design, you have to steer a lot of qubits before you actually do the computation. Now, whether you do measurement during state preparation or not, as I said, once you do quantum computing, the people who work on quantum computing, most of the people always stay here. They don't talk about state preparation. They don't talk about measurement. As I showed, state preparation is a difficult problem. And similarly, measurement is a difficult problem. And specifically, we know things are very noisy, and measurement is also noisy. So many of you will see papers where they're saying, well, we got 10x speed up or 20x speed up in computing. But then you want to ask them, well, how many times you have to measure? You got 10x speed up, but then you have to measure it 1,000 times and then take the max, mean, whatever. Then all the speed up 10x you are saying, actually you got 100 times slowdown. You didn't get a speed up because measurement time has to be included in the story. So measurement is very noisy. You cannot expect you just compute and measure once and that's it. You have the result. It's not going to happen. So question is, how do you accurately determine the result with few measurements? So before I talk about it, what exactly happens today? So when you are doing a readout, and then the readout you are passing through a discriminator, it's called discriminator. Think of a machine learning model, classical machine learning, and that's trying to say, well, this readout looked like 0, this readout looks like 1. And after you looked at all of them, then basically saying, well, I think the value is this because I have so many zeros. I think the value is 0. That's basically the story. You need n classification to find the result. So what Daniel is saying, well, if you look at the story, first, you are looking at the same qubit and the other qubits you are talking about, they are correlated to each other. Together, they're solving a problem. So we need to look at all of them together. We need to take a distribution, and we call it cumulative distribution function, and then do only one classification. So that's basically the key idea here. So instead of treating each of them as an independent data and then trying to make sense what they are doing, they actually represent certain behavior. Let's capture that behavior as a distribution function and do a single classification to know what it is. And if I want to give a layman's illustration, in a traditional classification, you have all this stuff, and then you try to figure out, well, this one I think is 0, this one I think is 0, this is 0, this qubit is 1. So my total all stuff is 0, 0, 0, 1, 1. And there is a significant chance of misclassification when there is a significant overlap. Whereas if you kind of do a cumulative distribution function, you are getting a much faster, more accurate result of the actual measurement. And as I said, the existing way of multi-classification could be expensive, low accuracy, whereas if you do cumulative distribution function, it's going to be high accuracy with few measurements. And again, I'm going to skip the details, but the key idea of cumulative distribution function is if you know the ideal curve or behavior of how 0 and 1 would look, and then you kind of know the function of when they're in a specific manner. When you get that, then you kind of know what is the target state right now. When you talk about multiple qubits, then we have a scalable solution. So we can generate constraints, and then we can use traditional classification that people are doing. And then if we merge constraints and traditional classification, then the quality of result is going to be significantly better than traditional classification. The act of constant generation for different qubit actually helps it significantly. And here are some results. Just to say, for a single qubit, we can reduce the mean absolute error by almost 78%. Even for multi-qubit, it's reduction in 12%. So it's not only we are reducing the error, even the number of times we need to measure, that also we are able to reduce drastically. So quantum error correction is actually a well-studied field for quite some time. It's very well-established field, and as the name suggests, it's basically similar to classical domain. They realize noise or error is going to happen, and how do you kind of correct it? But unlike classical domain, you have different kind of error correcting code, and the distance of the code and all that stuff is important. But in we can't use them in quantum computer, because the moment you measure somebody, it collapses the state. And we also cannot copy the information. So the idea of error correction, that you keep a backup or keep redundancy and all that stuff, doesn't work. Instead, in layman terms, quantum error correcting code, the way you work is that you construct a logical qubit, or logical error tolerant qubit by using few other qubits, 3 to 5 qubits. So think about it. You want one reliable qubit, you should be willing to pay another 3 or total 4 qubits. They together maintain the information and resistant to noise. That's the idea. And there are many kind of error correction techniques and many studies, and surface code is basically kind of state of the art, you may say. And in the surface code, it kind of layman terms, it constructs a structure with the qubits which I was talking about, and different kind of structures it forms, and that structures actually it makes it fault tolerant. And our recent QC work, Daniel showed how you kind of control those structures in an effective manner. And as I said, there are a lot of work on quantum error correction, and surface code is just one such example. And even then, in fact, if I recall it right, in recent QC conference, there was a whole session dedicated to surface codes. So next, I'm going to talk about quantum verification. So the idea of quantum verification is the following. So we are looking into two objectives. One objective is which I talked next, which is how do you know quantum computer is doing what it's supposed to do? And so that's kind of the ideal story. When you think of quantum verification, that's probably what you're thinking. If I'm computing something in a quantum computer, how do I know it's actually doing quantum computing? How do you actually know it's not somebody is not running it, some classical computer sending you the result back and charging you the money of running in a quantum computer? How do I know that? But then there are other problems also which are known as quantum verification problem, and which is similar to classical domain. If you have a parameterized circuit, or you can call it specification, and then you have a compiled circuit, which you can call it as implementation, how do you know that during compilation step there were no errors introduced? They are equivalent. Of course, the definition of equivalent is slightly different, but nonetheless, the end result is same. Or is it going to produce the intended result? Whatever the in our case of clustering, are they going to put the same set of nodes in the same cluster or not? Or if I ask about one of the node 5, would it be able to tell me, yes, it's in cluster 1 or cluster 2 correctly? In between, if it makes a lot of mistakes, I don't care. So that's why what's the objective is slightly different, but you are trying to see how, whether those two circuits are different. So that's kind of equivalence checking problem. There are solutions people are looking at by doing Clifford approximation. So because some of these gates, the dimensions are really, really expensive. Those of you are analog domain, you would be able to relate to it. So for example, in classical domain, when we do equivalence checking, model checking, we have discrete values, 0 or 1. Even then state space is large. If you go for an analog domain, there is no more 0 and 1. It's a continuous function. So model checking would discretize some of those. So for example, if I have a input variable or some sinusoidal waveform, you can't do check that output with another output. You have to discretize it on different timestamp. And as you realize, you are kind of doing an approximation. And that's why the false positive, false negative you have to consider. You are looking at 0, 1 or whatever values at different time steps, because there are infinite time steps. So complete correct answer model checker cannot do. So same analogy applies here. These qubits have a huge dimension to compare. And once you kind of replace those gates using Clifford gates, then suddenly it becomes much easier for you. Of course, you are abstracting. You have to deal with false positive, false negative. But now that you have Clifford gates, things are tractable in terms of different types of comparison and verification and testing and whatnot. So that's the quantum verification problem. And Daniel's recent works looks at can we do runtime verification. So this is another type of problem what I didn't talk about, which is, can I put a checker, runtime checker in the system itself? When I'm writing my quantum circuit, can I put concurrent assertion in there, which is going to check certain types of behavior I don't want to happen? It could be security behavior, functional behavior, quantum behavior. How do I do that? That's going to check during execution. And then there are many other types of testing and verification scenario. My final topic is on quantum security. I'm going to take 2 minutes and then I'm going to stop. So before you talk about quantum security, you want to think of how we are using today. We as user, you, me, student, professor, engineers, most of us, or except the people who are working in IBM Quantum, Google, Rigetti, and those quantum groups, we don't have access to the physical quantum computer. We access through cloud. So therefore, we kind of transfer our job through whether Amazon AWS or IBM Cloud. We are trying to access Amazon bracket, I meant Amazon bracket, and all that access we try to access. And then depending on whether we can generate pulses and provide, or we have to just run, give the quantum circuit, it computes something and it returns back. So then there are a lot of security, authentication, attestation, storage. How do you know when result comes back? How do you know it was actually run on a quantum computer, not on a classical? Remember, your job is going to be on a queue. And so you can't just look at the runtime and figure out, well, in classical, it would have taken 10 minutes. I got it in 10 seconds. You can't do that. So how do I do that? But then there are a lot of other types of attacks that's possible. For example, in this example, you ran some program through cloud, and then I'm running on the same computer, assuming I'm using the same set of qubits. Although the system is supposed to do a reset on the qubit, and that reset, let's say, didn't work properly, then if this is, I'm the attacker, it's my code, you are the victim, your code or your quantum circuit ran or used this qubit. Based on the residue, I'll be able to figure out what happened before. So this is analogous to cache side channel attack, cache-based side channel attack, cache timing attack, for example. So analogous, but this basically this state retention is a one possible attack. Similarly, when you have multiple qubits, maybe you are running on qubit 0 and maybe reset did happen. Now I'm running. Then even if we are not running same time, then I might be able to, based on crosstalk, because remember qubits talk to each other, and so depending on the crosstalk, then I might be able to figure out. And in the future, unless it's happening already, it's possible when you have a lot of qubits, IBM or whoever is selling through Google, they might be saying, well, I will allow both Mishra and Daniel and Hanrui to run programs at the same time, because you have so many qubits, they'll be running next to each other. Then these problems become even more. They're running at the same time. Of course, there are a lot of solution mechanism. How do you do reset? How do you do all that stuff? And Daniel also looked at, surveyed a lot of security vulnerabilities or how to solve them using secure classical quantum systems. But this is kind of a very new area compared to quantum error correction, quantum machine learning. Quantum security is like as old as 2022. No, actually 2 more years, like 3 to 4 years old. So there is a huge opportunity to make contribution in this area. That's pretty much all I have. Now I'll be happy to answer any questions.